All right. Okay, if it's fine for everyone, Rilong, yeah, you're connected. Jorg as well. Camille, perfect. I had a good look. Perfect. Great. Yeah. Whenever you are ready. In the meantime, in the first minute, I'm just so that you know, I'm gonna poke those different guys so that if some of them wanna join in the meantime, they can. Okay.
Okay.
Go ahead, Jonico. Yeah.
Yes, thank you. So I will just maybe shortly introduce Caribou and myself. I did a PhD the last 3 years. I just defended last November. So my thesis was on developing new methods, so new numerical methods to simulate soft tissues for surgery simulations. So it's right in the middle of the main subject of SOFA, I think, one of the biggest. And for my thesis, I looked around with meshless methods, for those who know them. So FN method without elements, so using neighborhoods of points instead of geometrical elements, your typical tetrahedral and hexahedral meshes. And I also looked at immersed boundary methods. So your typical finite element mesh, but that now allows the boundaries to lie within the elements. And for this, I had to implement a large broad of element type. And for those who know, in SOFA, that means that I had to re-implement the force field for each new element type or each new integration scheme, each new interpolation scheme, and for every hyperelastic material. So I had to re-implement all of these each time. So that's a lot of combinations. So we quickly, I would say, change direction and try to implement a plugin, Caribou. It is still, I would say, not really a proof of concept, a little bit more advanced than that now, but it is still very alpha stage, at the alpha stage. I mean, the biggest part of the development happened just 1 year ago at the beginning of the first confinement, so it's still very, very young. But yeah, so that's, I would say, a very quick introductions to Caribou. So it's not a bulletproof libraries that had the decades of development from different, no, it's me that prototypes a lot of things, often at the last minutes to get before publications or, so yeah. But still, I think it might interest some of you guys. So Caribou, it's in fact two things. You got the main library. I just want to check if I can get that pointer. Yes. So the main library here, which only depends on Eigen. And if you want this VTK loader here, you will also need the VTK library. Everything else is pretty much without any external dependencies. And then you have SOFA Caribou, which is built on top of Caribou, which brings SOFA components. So really components that you will add in your scene file. So you have tetrahedron elastic force and hexahedron elastic force. These are linear elastic components, which were the first two that I implemented, and that will soon die, I think so, because then I implemented a hyperelastic force field, which is templated over the element type. So you don't need to duplicate the hyperelastic force field for every element type you have. And I will show you how I did it soon. Basically, you will put this hyperelastic force field in your scene file, and then you will choose a material. Right now, I only have two, but it is very easily extendable. especially if we come up with some things with the Phoenix that will let us find the derivative of the energy functions of these materials. Anyway, for those who were there just before. And then I have a couple of linear solvers, which use either Eigen or Paradiso as a backend. ODE, so time integrator, yeah.
Just about this part, I think it's related more to the matrix session that we had before,
yeah,
which is related to assembly of the system matrix in SOFA, and then manipulation of those matrices and resolution in the ODE solver. I think at the end of the journey, this could be removed somehow from or cleaned and merged between what is in Caribou and what is in SOFA.
ODE, this was last year, so now I have a backward Euler time integrator. I will soon have a generalized alpha and a Newmark integration scheme. These support nonlinear elasticity, so they have Newton-Raphton embedded inside of them. Yes, SOFA Caribou are SOFA components. So all of these, I made these XML names here just to say you can put them in your scene files. Okay, yeah. So I will just go very quickly over the geometry model. So this was what I did to implement different kind of elements. These are your typical ones. So you will. These are C++ elements. So they are structures that you can template over the dimensions. So a segment could be put in a 1D world, a 2D or a 3D one, and you can specify the order. So it is linear, quadratic. So these are the one that I've implemented in Caribou, but I will show you, you can easily implement your own element types. The only things that you need to set when you implement an element is, well, first, this first structures here, which will give traits. This is a C++ template thing, so I hope people will be able to follow, those who are not very, I would say, comfortable with C++, but let me just say, the structures here will define some properties of your elements, such as its canonical dimensions. So how do you write a coordinate within your reference element? So for example, a triangle will have a canonical dimension of 2. So you have a 2 dimension of a triangle, but you could put a triangle in a 3D world, right? So there you have its dimensions right here, which will be its current dimension. And this will define actually the position vectors of each node of your triangle. So a triangle that is in 3D will have 3-dimension coordinates for each of its nodes. The number of nodes at compile time. So for a quad, you will always have 4 nodes. But for a point cloud, you might have a dynamic number of nodes depending on the size of the kernel of your point cloud. So this could be dynamic, -1 will be dynamic. And the number of quadrature nodes, so the ghost nodes, how many do you have, that is known at compile time. So for those who were there before with the presentation of Jack Hale, that's just to in the future give more hints to the compiler to be able to optimize the code. So if we know that we will loop on 4 quadrature nodes, if we know this at compile time, then the compiler might actually optimize this loop. And I don't want to do it. I want to let the compiler do it. So this is why I have this type of information. It is very much inspired by Eigen, which does something very similar. And then you have to implement these 3 functions. Get L, which will give you for a given local coordinate. So this will be in canonical dimension. It will give you the shape value of each node at this local coordinate. Then this derivative of this shape function. And finally, it will give you the each quadrature node, so the Gauss node, the local coordinate of each one of them and their weight. So again, this structure here will be used as a template here in the template argument of element. And it will enables a couple of functions over your element. So I have binded this code with Python with PyBind 11. So if for example, if I create an hexaedron element from a set of nodes, I can automatically get its center point. I can get the world coordinate of a local point, so a point within this hexaedral element. Oops, sorry. I can do the inverse transformation for nonlinear elements. This will do a couple of Newton iterations to find this local position. So basically, this will let's say you have this hexaedral element, you have the position of a node somewhere. It will find the local coordinates of this node within the element. Okay. You can get the Jacobian of this transformation, again, at a given local coordinate. You can check if it contains this point. And then you can interpolate a function and integrate a function over this, this element. So this will simply, for example, the integrate will loop over the quadrature nodes and compute this function here at the location of the quadrature node. So yeah. So I hope this is clear. This is the geometry part of Caribou. And then you have topology. That was 1 year ago, but basically a mesh in Caribou contains one or more domain. One domain can only contain one type of element. So you can have a domain of tetrahedral elements, you have a domain of triangle elements, all within the same mesh. Okay, so the element node indices here are relative to the node position vector, which is in the mesh structure. This is again templated, so domain is a header-only file class, so it will hopefully get optimized by the compiler again. But this domain will allow you to interpolate, but for example, a function, but this time over a complete mesh, so a subdomain of a mesh, okay, instead of just one element. So an example here, it's in Python. I'm loading the mesh of a lever here, which is a VTU, so it's a VTK file using mesh.io. This is a very handy Python module. If you don't know it, it can read a lot of mesh types. So I'm reading this mesh. I'm reading also a vector of displacements that were found, for example, using SOFA or Phoenix or some other simulations. So that will be the displacement of your lever, the deformation. And then I will create my mesh, my Caribou mesh. I will add a tetrahedral domain to this mesh. And then I can put some embed position within this domain and go interpolate the displacement at this place. So this is typically what you would do in a barycentric mapping of SOFA, where, for example, you have your lever that is modeled with a tetrahedral element, and you have, for example, some vessels or tumors that are within this lever, but only for visual purposes. So you just want to map their positions. Well, this last line will do this for you. So it will interpolate the displacement over the position of the embed position, and then you get the displacement for each of these points. Okay, so this is, I mean, it was super useful in the case of our research where we would run a lot of simulation and afterwards go get this displacement at some markers, positions, and estimate errors yeah. So this is one of the things that the domain can do for you. This is not finished yet, but the idea here was, again, I have a domain, a Caribou domain. This is this time in C++, but you can do the same. You should be able to do the same in Python. And the idea here was to assemble a given function. So in this case, the way this was the initial idea, now we are moving towards a signature of this callback function that is a little bit different. What you would get here as the arguments of your Lambda function would be, how would say that? Okay, I will reformulate a little bit. What will be executed within this Lambda function is what will be evaluated at an integration point within your element. So what we are aiming to do next is to actually, I'm sorry, I will have to do it here. It's to pass, for example, a field, a vector field over each node of your domain here. So for example, the displacements over each node. And the Lambda here will return you the interpolation of this displacement at the coordinate of the Gauss point. Okay, so basically what you will do is you will use this interpolated displacements to compute, for example, the stress or the stress of your function, and basically using Caribou, you would want this to assemble this into your vector R here. And at some point do the same thing for your stiffness matrix. This was really an idea. It's not finished. We have an idea how to do it for a residual vector here, but not yet for a stiffness matrix. But basically for those who implemented add force and add K2 matrix in SOFA, you will simply have this in your add force for a linear elastic material. You will get F, then you will get your right Cauchy-Green tensor, you will compute the second Piola stress tensor, and voila. And the domain will get this and assemble these over the test functions of your domain. So we are getting closer to this. Now the SOFA Caribou components don't use this. They will loop over each element type. I might show you after that. And they will do these computations for each Gauss point manually. Okay.
I think you're answering somehow to Rilong's question, which is, does that work only this way in Python to assemble yourself your matrix, or can you run a scene within which it will, a SOFA scene?
You can use your typical XML scene. Of course, now what I'm showing here, it's only Caribou. It's not SOFA Caribou yet. Okay, so this can only be used either in C++ or Python if the relevant function have been binded in Python, which most have. Yeah, so I have the same thing with in Python here. And then for SOFA Caribou, this might be a little bit old. I had a new one that I made yesterday very quickly. I'll just check if I can get it. And you will see that you can, in fact, use it in XML. Let me just try to find it.
The idea of those libraries, Caribou libraries, like the geometry part, again, later on, the idea would be that this kind of approach would be available in SOFA directly. I mean, I think that's the philosophy we want to go. But these are libraries, and on top of those libraries, there is one which is building SOFA components following the design of Caribou. That's SOFA Caribou. SOFA Caribou includes all the components following this design.
Yeah, exactly. Let me just, can I get, I don't have the scene, but I might just jump into the Caribou source code just to get a very quick demo. So if I go in a scene file, for example, yeah, backward rulers might be just, okay, hyperelastic force field. So let me, can I zoom? Damn it, I should have done this before, but can I get the zoom? Oops. Zoom, numpad plus. Doesn't work. Sorry for that. It's another PC.
In the view panel, I guess in the view panel, you should be able to, in the view widget here, you should be able to zoom in. Usually it's there. Appearance.
A lot of option.
Here.
Yeah, there's full screen, etc. Usually I can activate the zoom. Let me just check quickly. If someone see it before me, let me know. Maybe editor general. I know there's an option that allows you to do it, but for some reason it isn't activated by default. Anyway,
I mean, we can
I
still.
hope you can see it.
I can read it. Yeah, it's not perfect, but I Control Alt S. See that he's saying.
Control Alt S. Scrolling. We have a change font size with control moves. Nice. Okay. Yes.
Yeah, perfect.
Can you see it? Okay. So for example, here I have my, so it's in Python, okay, but I'm just building the scene file in Python. You could do the same thing in XML. So yeah, instead here, the static solver would be just written as this. Anyway, you get the point. For example, 10 Newton iteration, and etc. Okay, so you could do the same thing in XML. And the idea here was to, this is still SOFA topologies. I'm sorry, I'll go with quadratic elements, so I'm sure no SOFA component have it. So I have, again, a quadratic mesh here, which is a VTK file that I'm reading using Mesh.io. And here I will have two components. So the tetrahedron 10 nodes tetrahedral elements and 20 node hexahedral elements. And I have my Caribou topology here, which will specify, using this template argument, the template name of my element. So this is something typical to SOFA. So template are C++ template are specified in their scene file using this template argument here. We could change this, but anyway. So the Caribou topology will have a set of indices. So this change from your usual hexahedral set topology container, where you will have this hexahedra data field which contain the indices of the hexahedral elements. Here it's just indices, so it will really depend on the element type here. Okay, so in this case it will be an array having the number of nodes as lines and 10 columns for each index of each node of your tetrahedral element. So basically 1 element per line of your matrix. And then you have the material, Sinvenant-Keshkov. I will show you later how you implement a new one. And you have the hyperelastic force field, which again is generic. So it will use the Caribou topology to build its stiffness matrix and its force vector. And then you have a traction force field, which also use the Caribou topology over the quadratic triangle here. And yeah, so this is Caribou, everything that has Caribou in its name. The traction also force field is Caribou, so it is independent over the element type. It's a template. Same thing for hyperelastic force field. So if I jump into the source code of, for example, the hyperelastic force field, I will see that in my add force, which is here, I will loop over the element. I don't know what kind of element I have here, right? If I go to hyperelastic.h, the header file, the definition of the class, you can see that it's templated over the element. And this element is what I shown at the beginning of the presentation. It's something that will inherit from a Caribou element, but that just define these 3 functions here. So if you have this, you can use it as a template argument of your hyperelastic force field. Okay. And then, like I said here, to compute this force vector, it will loop over each element, and then over each Gauss node, it will compute. So these one are stored, they are computed at the beginning of the computations, but it will compute your deformation tensor, your stress tensor, and then it will write the forces on each node. So that's basically the assemble function that I would like to see more generic in Caribou. Okay, but this is done manually. At least it is for any element types. Okay, so you don't have to re-implement this force field if you want to add a new element type, a cubic one, for example. The other thing I wanted to show you, so mappings work the same. I have barycentric mapping. I show it here. I don't have it here. It's a new one, but yeah, the material. This is what I want to say. Material. So basically, a hyperelastic material. They will have this strain energy density function that should return a scalar. They also have this second pillar Keshkov stress, so it will be given the right Cauchy-Green tensor at a given Gauss point, and it should expect this stress tensor at the same Gauss point. And you have the Jacobian of the stress, so again, it will receive this right Cauchy-Green tensor, and it should get a symmetric version of the Jacobian, so only the 6x6 matrix. And this will be used for the add-create matrix of the force field. So basically, these things could be written in Python. I didn't have time to bind them in Python yet, but it should be very, very straightforward. And hopefully, at some point, you would only have to write down the strain energy density function, and the stress and the Jacobian of the stress should be found automatically with automatic derivation. That would be our ideal, I mean, our goal. That would make us very happy, because finding here the Jacobian of the stress for some very complex hyperelastic material, it's not easy to. Yeah, and I'm really improvising here because I didn't present anything, prepare anything. I wasn't aware that I needed to present. So there's validation here. I have Phoenix, some Phoenix script to validate my force fields. I have also FEBio for those who know them. It's using Docker to run these validation scripts. I also have manufactured solutions. So it uses SymPy to generate a manufactured solution and validate the force field of Caribou over this. I have unit tests for both Caribou and SOFA Caribou. So that's probably the best place if you want to use Caribou to look for examples. Of course, you will find some G-test or unit test lines, but I guess you can quickly get what you want by looking at these tests. Like there's a lot of example. I pretty much added unit test over every function of Caribou. So and yeah, I think there's the doc, so documentation. You can find it on Caribou. Let's read the docs that I yeah. So at the left here, you have every SOFA component that you can use. So if I go in the backward Euler, you have this that you could use either in your XML or Python scene. You have a quick documentation. You have the attributes for your component. And a quick example, so in XML or Python. Python binding, so I don't have any for the backward Euler AD, but if I had, it would be here. For every component, you have a link here to its doxygen. So you can click here. Not sure if, yes, I put it there. So then you find the doxygen of this component. Yeah. So that's it for the overview. Very, very quick overview of Caribou, but it's basically this. It was really written to easily prototype different kind of elements, either immersed boundary element, extend XFM elements, meshless methods. So it was an easy way to don't have to duplicate this hyperelastic force field for every kind of discretization method you had. So yeah.
Thanks, Jean-Nico. And yeah, to extend a bit what you said, there was a question from Rilong. You can check if I answered properly. But the reason why we decided to set up this session is also to make again Caribou. We already talked a bit about it last SOFA week, and again to talk here about it today because first it continued and there have been further development led by Jean-Nicolas. And the idea is also that if some of you guys want to, appropriate this work and pursue it and collaborate with Jean-Nicolas in the implementation, we thought it was a good timing for that, a good moment where the plugin starts being quite, I would say, dense, as you can notice. The way to manipulate it is also pretty various. You can work with it from Python or from C++. And yeah, we are Alexa.
Yes, it brings me this question: what is the future of this plugin? So, is there anyone planning to work on this one and maintaining it, or adding more features?
So we just add the Go, and Hugo will just stop me if I'm about to say something wrong. But we just add the Go to get a license, an open source license, because right now there is no license. We were still trying to do it with INRIA, but now we have to go, so it will probably get the same license as SOFA. And it will get into SOFA framework repository. At Mimesis, more and more people are using it. So on the development side, I'm not sure I'm able to answer you, Alex. I really don't know. I hope some developers will want to contribute. I mean, the idea here was to get the least amount of components possible to do the more of the things. So for example, one hyperelastic force field would be able to generate a lot of hyperelastic FEM simulations. So that if someone have an idea to change a design, or for example, for the stiffness assembly or things like that, he can just change the one component and it should handle all of these cases automatically. I guess this is one of the strong points of Caribou. Maybe it could also, like this was really a prototype plugin, so maybe it could, I don't know, prototype the new architecture of SOFA for these force field or for the elements, the topologies and things like that. So I hope maybe it will inspire some things like that to help them prototype very quickly before bringing it to SOFA. So yeah, because for people who are here, I guess why Alex asked this question is because I will leave soon. In 2 months, I'm going back to Canada, and I will have to change jobs because Enria is French, and yeah. So I hope I will still be able to work on this. I see, Jack, there are some C++ source level automatic differential tools that support agents. That could be very nice. I'm really not aware of any of these tools. I know, didn't Egan at some point try to do it also directly? But anyway, I think it would be very great to look at this. Yeah. But,
what's the name? Yeah.
there was also this idea of topological change, right? If I go back to my add force, but even in the update stiffness, right? Here I'm looping over each element and then over each Gauss node. If you were to have topology elements that allow us to assemble, so get your nice callback function that would just execute this here for each integration point, we could let this topological component handle the topological changes so that this force field doesn't care about what is currently happening with the underlying mesh. It just set this callback function, but the topology component is doing the hard job of propagating the different quantities on one element that has been split into many, or that will delete some data fields over these elements. So that will be the job of the topology. But from the force field point of view, it would be awesome to just not care about this at all. Just loop. Either loop over the elements or get this callback function that will be called for each integration point. That was also one of the ideas we had.
I don't know if you noticed the question also from Maxime, which was a bit above. What's the story regarding compile times?
So, of course, with everything templated, it's always a little bit of a, yeah, I would say you always have to be careful. Here, as you can see, you have these explicit, I followed the idea of Damier for those who know him, where you specialize some domain. So everything in Caribou remains template-based, a header on D. But when you get into Caribou, then you will specialize over some type of elements so that you only compile once here. So it's not that bad. Hopefully, this assembling could be virtual so that you don't have to template specialize for every of these types. So for example, a hyperelastic force field here, if you go over the header, it will only extern template, so force the compilation of this hyperelastic force field with the template hexahedron, linear and then quadratic. And if you go into C++, it does absolutely nothing but to add them to the object factory of SOFA. So there's no code, no computation done in this specialization. They are only there to tell SOFA that they exist. Okay. At some point, we could even remove the template over hyperelastic force field. Hyperelastic force field could just look for a Caribou topology or a topology component and call its virtual function assemble. That would be even easier. That was one of the ideas we had, but right now it's just the current design, so it can change, of course. And but yeah, so basically I will force the compilation of big components over one element types, and that should decrease the amount of compilation time, hopefully. Like I said, it's not too bad. The bad thing happens when you do Python bindings, because then you have to do it for a different type of int, a float, of different type of elements. So it gets quite messy if you don't want to copy data from, for example, NumPy to Caribou. You actually have to compile for each of these types, so it gets messy very fast. But this is the Python side. So only for SOFA side, the completion is not too bad.
The next one was a question from Jörg asking for higher order element, figuring out what elements overlap is non-trivial. Otherwise, many zero entries are computed. Is this optimized?
I'm not sure I understand. Figure out what elements overlap. Jörg, can you take the mic?
Yeah.
Maybe.
It's especially the verb overlapping, which I'm not getting here.
Yeah.
I don't see.
Do you talk about the mesh? Because of course I'm not playing with the mesh at all. I'm expecting a mesher to mesh the domain.
And to mesh it properly.
Mesh it properly.
And then we don't get add another question.
Sorry, I only just managed to figure out how to get the microphone
Yes.
from non-microphone.
Sorry, the interface is not super
complicated. So my experience has been that building the matrix, if you build it at all explicitly, but the expensive part or the difficult part is to figure out what entries are non-zero in the matrix. If you have higher order elements, they'll overlap each other. So if you have splines, and so one might be talking to 25 neighbors. That's not so much the case when you have first order elements, then nothing much is happening. You just talk to your neighbor. And so the expense is in computing only those integrals or forms that are actually needed.
Are you talking like for meshless methods or things like that? Or because for like hexahedral meshes, I don't see where you get the overlap, or maybe I'm not understanding correctly.
Shape functions should, yeah.
Yeah, so it's not a matter of whether it's hexahedral or tetrahedral or whatever, but a matter of the element that lives on this kind of partition. If the element is restricted to the element, if the function is restricted to the element,
yeah,
then it's no problem. You only talk to your neighbors, if at all. But if you have higher order, then you have a submesh that is overlapping another submesh. And now you get all these. So the background for this is isogeometric analysis, where this happens all the time, where you have an additional kernel between your f functions, and you have finite elements that are relatively far from each other, but still interacting, and without which you will get the wrong results.
Yeah.
And I wonder whether that's something that entered into these discussions. If you just have lower order elements, then I think that's not a problem.
But yeah, it's also that I only have Lagrange elements now. For meshless, I had these problems because your shape function, for meshless, we had this integration grid, which is, I mean, we usually use an X grid. And then you have these point clouds that will define your interpolation scheme, and these will overlap. But in these cases, there were not much that we could do except try to reduce the kernel, the radius of the influence and things like that. But nothing that I could do automatically, or that was really not my field of research.
Okay.
We were playing with it manually. So that was building the discretization of the domain with, hopefully not having too much of these overlaps, but nothing more advanced than that.
Thank you.
Sure.
So I think I answered to Younes properly. There is Maxime asking a question, and
there's Julian also macOS and Linux.
Yeah, my question is simply that so I went through the GitHub page of the Caribou, and I see that there are some items that specified for Linux and Mac OS that's working. So I'm not sure if it's fully working for Windows.
Yeah, it is now working thanks to Eric Bernot. So now it is compiling in Windows. The unit tests are running. I just didn't have time to add the GitHub workflow file to run the unit test automatically on the CI, but it should work fine. Yeah.
I think my currently the SOFA repo I'm working on is 2012.
Yeah.
And I followed that. I think you mentioned the SOFA Python 3 is required to build that Caribou. So I followed.
It is not. It's not required. So you don't have to build SOFA Python 3. You can use SOFA Caribou without it. Normally the CMake will detect. If the CMake detects SOFA and SOFA Python 3, it will compile the SOFA bindings. If it doesn't, then it just won't compile it, but SOFA Caribou will be available.
So I can directly compile SOFA Caribou instead of first compiling the Caribou. Is that?
Yeah, but Caribou is mostly header only, so you won't have anything to compile here. Unless you're using it in your project, you won't have anything to compile with Caribou. It's SOFA Caribou that will get compiled into a plugin, an actual library.
Okay, yeah, that. Okay, I earlier thought that Caribou itself is a prerequisite for SOFA Caribou.
Yeah, it is a prerequisite. So SOFA Caribou will use it. It will use the headers of Caribou.
So I don't need to compile the Caribou, and I only need to compile SOFA Caribou.
Yeah, it will use Caribou unless you are compiling the Python bindings. Then of course you need to get these nice Python modules. But if you are only interested in SOFA Caribou, then it will compile directly. Yeah. Of course, you need to provide the path to SOFA.
Yeah, thank you. I will try it one more time, just to, so I don't need to compile the SOFA Python 3, so I can remove it. Yeah, so yeah, I think thank you. The Caribou project sounds to me a very interesting one that I want to work on.
Okay.
So as I briefly introduced my work yesterday, I was trying to add the hexahedral elastoplasticity model, and currently I only add that to the existing hexahedral IBM in SOFA.
Okay.
So so I want to see.
That would be great, because it would be a nice test case of bringing in another equation, so the plasticity, and hopefully if it works well, you will only have to do one force field that should work with every element types. hopefully. So it would be a great addition. Yeah.
Okay. So in SOFA Caribou, in the force field, so I see that there's a hyperelastic force field for hexahedron. So what? So you suggest that I will look into the
Yeah. So
hyperelastic?
yeah. Just look the tetrahedron elastic force, and there's the hexahedron one. These were tests that I did. These were the first two components I did in Caribou, just to know if I understood correctly at the beginning of my thesis. So they will get destroyed soon. I just didn't have time to do it. But they do exactly the same thing as the one in SOFA. Okay. Ideally, at some point, we could have a linear elastic force field, which is made the same way as the hyperelastic one. So that is templated over the element type. But yeah, I just need to do it. But that's the idea. And I guess the point here is it is still there's still many ways to improve it. Maybe change a little bit the design. It's still in alpha stage. So if you see some problems or improvements that you think of, for Jorg, if you had a better, if I didn't understand your question correctly, but if you see a way that we could improve this in Caribou, I mean, it's a good playground, I think, to testing within SOFA. So.
I said there was gonna be a question from Maxime, but finally he stopped typing. He's gonna activate his mic. Yeah, should be incoming.
I have other things. I have like a eigenmatrix, which is kind of a new version of the eigen2 matrix of SOFA. It's a base matrix that is templated over an eigenmatrix type. So you can interface with SOFA with it. I have the same thing for eigenvector. So it's a SOFA-based vector. And basically, you just write an eigenvector, and the template would be the eigentypes you want, so sparse or non-sparse. And you got the specialization for sparse matrices here. But sorry, I might zoom it. But yeah, so it's there are some tools function or visitors that you can get also that I needed to implement.
Maxime, go ahead. If you like.
Can you hear me?
Yeah.
Yes.
Yeah.
Cool. Thanks. Very nice work. It seems very promising. I was just wondering whether you are familiar with this old plugin called Flexible.
Yes.
That was, yeah. And how does this compare? Like I assume your work is way faster than Flexible. And I was just wondering if you have some feedback on the.
I would say my biggest feedback is I tried using Flexible and understanding all those mapping between different quantities, kinematic quantities, and yeah, I mean, I cannot comment really on the code of Flexible. I mean, on the how Flexible performs or allow us to do, but I had a very hard time getting into Flexible and experimenting with different shape functions.
I know what you mean.
Yeah, so I stopped there. It was at the beginning of my PhD that I looked to it, and I was kind of spending more time trying to understand Flexible than the theory itself. So
okay, I see. Just maybe for the others, Flexible was designed by one of my colleagues, Benjamin Gilles, and the goal was to expand all the computation for integrating potential energy in a deformable solids as a sequence of mappings. So you would get from the node degrees of freedom to the deformation gradients, and then from the deformation gradients you compute the the strains and with different kind of strain measures. And then you would have some material low as a force field, but at the very bottom of your scene. So you could switch any stage of the computation, even at runtime. I mean, you could do that, but maybe you don't want to do that. But yeah, so you get this kind of flexibility, modularity that I think you get from your work, but it's all runtime and mappings, and of course we need to assemble all this kind of this mapping chain, and your work is way faster because the compiler can see everything. And
that was the
I
main
think it's,
idea. Can we get
yeah.
this flexibility while letting the compiler do its wonderful job of optimizing this? And it was also, can we see this this nice equation that we have on paper? Can we see it in the code? That was one of the main thing we wanted at the beginning also. So can we read this equation as we are able to do it with Phoenix? Can we do it also in SOFA's code? That was also something we wanted to do. Yeah.
Cool. Very nice work. Thanks.
Thank you.
And while waiting for Tammy comments or question, I think it's also related to Alex's remark. That's really something where we need to get people leveling up to mastering the plugin themselves and getting really into the code, as you said, daring, adding stuff, modifying things here.
Yeah, just go play with it, break it. Like I said, it's a playground. I use it for my thesis. I mean, I broke it so many times. It's made for, there's a lot of unit tests to make sure you're still okay. So go ahead and try it. I think it's worth it.
Is there differences in terms of performance with SOFA?
So I never, I mean, I did not really benchmark it like in a proper sense. The way I did it was like starting a scene with the SOFA component and Caribou one and looking at this graph, the advanced timer. That was my way of quickly benchmarking it, and the performance were about the same. Now, obviously, this is hyperelastic force field, so you can only compare the tetrahedral one with the one in SOFA, which is a tetrahedral hyperelastic force field. And then again, you don't have other elements type than tetra and hexa unless you go with the SOFA high order plugins, I think, right? I never tried it, but I guess we could compare. But then can you do hyperelastic with quadratic elements? And yeah, I'm not sure.
I'm not sure neither. I'm not sure. I don't remember.
Anyway, and with this, you also get the barycentric mapping. So that was a big question we had here. Can we still map tumors inside a quadratic mesh? You can. There's a barycentric. So it's not barycentric mapping. It's something I just finished last week, and is show you because if you try it now, it is here. It is a pull request that just passed the test. So I just wanted to add it to the documentation and then hit this merge button, and it will be available. So basically. I think I have a scene file, an example. The test, where's that? I'm pretty sure I have scene file. Yes, very something. So yeah, here you have it. So you create your scene. As usual, you have your Caribou topology. Maybe can I zoom it? View file. So there it is, Caribou barycentric mapping, for example, for a visual model, an OGL model. So this is linear triangle mapped into quadratic. Actually, I have many meshes. So I have P1, so a linear tetrahedral mesh, quadratic, trilinear hexahedral mesh, and the quadratic one. So basically it will create one beam per mesh, and it will map a cylinder inside this rectangular beam. So the beam will bend, and you have the barycentric mapping for the visual. So this will be available as soon as I hit the merge button, which should be this week.
Cool. And thanks for your answer. Actually, I was asking because for me, this way of implementing things is way clearer when you want to modify the material behavior or look at nonlinear elasticity, plasticity. And yeah, so I was wondering if this makes really a difference in terms of execution, or as maybe we can expect no. And in this case, I find it very interesting for that particularly.
It should give the same things as SOFA. SOFA, there are some places where they try to optimize, try to do what the compiler usually do, I think. So sometimes you will read a force field in SOFA and you will see a bunch of unroll looped. I did not do that in Caribou. I suppose the compiler will be able to do it. So if it's not able to do it, maybe I lost a little bit of performance there. But yeah, the idea was we should accept maybe a little bit of performance hit if it can improve the code and I mean allow people to easily implement things in Caribou. Then it's I mean it should be more important than this small hit of performance. Now, if it's a big hit, of course, we need to think about it and maybe redesign some things.
Yeah, but a small one makes sense, in my opinion, as you said, like to get this clarity in terms of implementing new behaviors, new materials.
Yeah, I think if it works, then if you really need something super optimized, then specialize one component to really do it and optimize it. But for Caribou, it was like, can we keep it generic and readable?
Cool.
There was another point. Yeah, I tried to reply to Ilong, about is that gonna at the end of the journey replace? I'd like basically to say yes, because there is actually many justifications, explanations that would actually push for that. The tests, the adaptability, the versatility of SOFA Caribou, for sure. But we really need to make sure as well that it fits really well the rest of SOFA, including firstly the topology. That's what I said at the end of Jack A's presentation. It does not mean that we don't want to. It's more a question of development forces. That's also why we are organizing those events like today, to have you around the table, to let you know that, I mean, it can definitely replace. I mean, I'm the first one to see the shitty Tetradon FEM force field. That was maybe perfect at the time, but nowadays, today, when we have students, when we have PhD students, even when we have researchers that want to get into the code of SOFA, as Camille said, they are just facing hundreds of lines of codes for only, if I can say that, linear elasticity, and they won't find anywhere somehow the equation appearing. So it's super frustrating, because it's giving the feeling that everything is magic, and as if it was super optimized, which is, I think, not anymore really the case. Caribou is definitely an alternative for that, where you could see the equation for mechanical engineering as well. Pure mechanical engineers, they would be as well a bit more confident to touch the code if they can see the equation. So it's going to close. Yeah, I see the breakout is going to close in 1 minute. We're going to be moving to the other room, the main room. If you have further questions, please do not hesitate to carry on.
So we'll be here also tomorrow.
Yeah, tomorrow there will be. Actually, we will talk about topology of Caribou, since it's one of the. But if you want to get involved, let yourself know, or just as Jean-Nico said, pull
Yeah.
the plugin, make pull request, break it, add it, improve
Let's-
it, whatever you want.
Of course.
So see you in 20 seconds in the main room, and maybe we can answer in the main room Wilong's question about sofa topology is currently independent of sofa topo. So
It
just to make
is.
it clear.
I can give you the quick answer. It is right now because
Okay.
there's, I mean, the API is so big in the sofa topologies. I didn't want to overload the.
And that's in Caribou instead
But-
of the sofa one.
Actually, you can use the sofa topology container.
Oh, okay.
You can use both of them. So the hyperelastic force field will understand both. However, you cannot use Caribou topology with, for example, sofa hexahedral force field. So with sofa components, because they don't know Caribou. Okay.
I see.
But
Yeah.
but the other direction is fine. So Caribou will understand sofa topologies, which only handles linear tetrahedral mesh and hexahedral mesh. And if you want other type of meshes, then you will need to use the Caribou topology.
I see. Yeah, that's good. So yeah, I will still use the sofa topology container.
Yeah. Okay. Great.
Yeah, and I will. I think I will try to fix my compilation errors today of the sofa Caribou.